be presenting nanometer scale thermometry, specifically in living cells. This is based on the paper by Dr. G. Cusco, which was released in 2013, sometime in 2013. And yeah, so what challenge are we dealing with? Measurement of temperature in very small systems in the range of nanometer is still an incredibly difficult challenge. And increasing the accuracy and sensitivity over a large range of temperature is required in different domains of research. And we specifically aim in this paper to deal with living systems such as cells or some biological dynamic system where the spin one system of the NV center can be utilized to measure the temperature. Now, already existing systems to measure temperature have either very big sensor size or the accuracy is quite small. The proposed method sits right in the sweet spot of a few hundred nanometers and can even be accuracy can even be increased more, right? So it can be used, let's say, near cancer cells to check how the gene expression is happening or what is the growth of the tumor and so many other applications. So we will be utilizing, like I said, the spin one system of the NV center where there is an inherent spin-spin interaction because of which you see a zero field splitting. So with the temperature that is causing the gap, we can detect temperatures as small as 1.8 millikelvin, which is very very accurate. And the thing is, this paper stands as a proof of concept. They utilize two different cases. My colleagues will talk about it, and we will be measuring around the length scale of around 200 nanometers. So this is the ground state and the excited state for the NV center electron spin. Like I said, the zero field splitting will already split the state into ms is equal to 0, and you'll have plus minus 1 state. Now the fluorescence from the excited state back is dependent upon the temperature, and any deviation in the temperature will be observed with the fluorescence. And for the NV center, we observe that this gap caused is dependent on the temperature, particularly a measured value. And if you happen to utilize some other material, then this dependence would have to be corrected. Giving on to
So we know that the zero field splitting is highly dependent on the external magnetic field we apply. To counter with that, what we do is we do spin echo sequencing, which would basically give us a free evolving time, tau, and that would correspond to a coherence time, which would maximize your sensitivity, basically make it better. To do that, we do spin echo sequencing for different time scales. For one, we do for 50 microsecond, and in another case, we do it for 250 microseconds. And we have this formula for sensitivity, which is 1 over c delta by del t multiplied by 1 over root t coherence nt, where c is a factor which basically gives your contrast or your how clear the imaging is. D delta by dt is basically the temperature dependence of this zero field splitting. T coherence is the time we're trying to find out, and n is the number of NV centers, and small t is your total time. So from this experiment, what we get is a corresponding sensitivity of 9 plus minus 1.8 millikelvin per root hertz, which was proposed before, and we get an absolute temperature delta T of 1.8 plus minus 3 millikelvins. So moving forward, what the experimental setup was proposed or would have been used in the paper is as follows. What we have is a confocal microscope from which we observe what is going on. We have lasers to heat the gold nanoparticle, and we have another laser which would basically check out the fluorescence. What happens is when we heat the gold nanoparticle, the zero field splitting changes as it is a function of temperature, and with that the fluorescence's wavelength would change, which would be captured by the camera. So the next part would be taken out by Dhruv.
Yeah, so we come on to the measurements. So the system what they created first was they implanted the nano diamond and the gold nanoparticle on a cover slip, and then so we need to measure the temperature variation of the zero field splitting, and for that we take the electron spin resonance signal consect at different times consecutively, so to get the wavelength variations with time. And then an additional measurement they did was they checked the variation of temperature with laser power. Yeah, so this is our ESR spectrum that we have. So we check the variation of these four frequencies by taking consecutively ESR signals. And so in this system, this is a frequency scan of approximately 500 NV centers. So a nano diamond has 500 NV centers in it. So what is happening is, so we have multiple ESR signals, and those four frequencies will now shift as the temperature is fluctuating. Yeah, so this is a confocal scan of our system. So this system is basically a cover slip, and the cross represents where our gold nanoparticle is, and the circle represents where our nano diamond is. The color bar represents the fluorescence, the fluorescence in counts per second, and we can see that the circle is red because it is emitting fluorescence. So variation of laser power with distance. So the first plot they did was they checked the variation of temperature with laser power. So we can see that they got a linear dependence with laser power. So they increased the laser power on the gold nanoparticle, and they consequently measured the temperature differences of the nano diamond, and it was seen that it was a linear dependence, the red line, and the blue line corresponds. So what they did was, if they wanted to check that the heating was only due to the gold nanoparticle and not due to the local effects, what they did was they in the second part in the blue line they changed the path of the laser from the gold nanoparticle, and in this case they did not see any temperature changes. The delta T is a constant. In the second part, they took the nano diamond and they placed it at 6 different locations, and we can see that it varies as a 1 over r dependence with the distance, and this is perfectly agreeing with the theoretical prediction. This formula delta T of r is equals to q dot by 4 pi kappa r. We get it this by solving the heat equation over a 2D surface. In the steady This is a steady state solution, so we can see this also has a 1 over r dependence, which is agreeing with the experiment. So Dhruvi will discuss measurements on a live cell.
Yeah, so to bring the final idea home, our main aim was to do temperature measurements on a living cell, right? So the next part, what they did was they introduced nanodiamonds and as well as gold nanoparticles inside a live cell using nanowire assisted delivery. And then similar experiments were conducted. Basically, laser was put on our nanoparticle, and heat temperature measurements were done on NV centers, and it was observed that the NV center that was closer to our heat source showed a greater temperature dependence, of course, because it was closer and it could measure over more accuracy as well, as compared to the NV center that was further away. One more thing that was observed was key. Uh, yeah, so the NV center that was closer showed more dependence. Uh, yeah. Now, incident power was varied over a few Kelvin temperatures, and the measurement of 5 Kelvin was observed over 7 micrometer distance inside the cell. Temperature gradient was to ensure that the temperature gradient was majorly due to gold nanoparticle and not some cytoplasm heating or something like that. The laser was moved away from the gold nanoparticle, and again the measurement was done, and the calculations ensured that it was basically what we were observing was the gold nanoparticle heating. One more observation was that high uncertainty was observed in temperature measurement, which was due to drifting of nanoparticles due to the power that was supplied by the laser that was there. Um, Now, when we increase the power beyond a certain threshold point, cell death was observed, which was confirmed using ethidium homodimer 1 assay. Now, this becomes an important side application as well, because then you can control the cell viability. So, if there's a cell that that I don't want in my system, then I can simply increase my power and cause cell death. So that was measured by applying 12 microwatt power and then 120 microwatt power, wherein for 12 microwatt power, a cell was viable, that is, it was living, and in the other, it was dead. So that's all. Any questions? Sorry, why do they use? Oh, so gold is a favorable material because it, like temperature-wise, also it is a inside a living cell particularly. It heats up more efficiently also.
So when we shine the laser source on it, a surface plasma resonance is excited upon it. So it is a non-radiative decay. So all the energy is converted to heat.
And so if you come back to the scheme that you had on the first slide, or the very first slide, the one with the gold nanoparticle,
Um,
yes,
Sorry.
the experimental setup.
Okay, okay, experimental setup.
No, this one.
Okay.
There is maybe something a little bit different. No, here it's not good laser.
They've just used two different sources, but in reality, you wouldn't need a separate laser.
I was thinking that it was slightly, it was pharmacology better. It was two different wavelengths.
Oh no.
The same
It was
laser.
the same laser? Yeah. Okay. Okay, maybe you do on one spot and the other on the other spot. Yes. Okay.
Also, gold particle is, in this case, they've written that it's specifically just to make sure that the heat conduction is really
Okay.
well. It is just to mimic another natural heat source. So
And do you believe that, for instance, I'm now interested in the properties of the materials of the heating? So if you go to the map of showing the dependence of 1 over R,
Okay, one over one.
okay, this one, there's this nice dependence. There's another parameter, it's kappa. Do you think that could measure it? Kappa.
Yeah.
Kappa. What is kappa?
thermal conductivity.
The thermal
Of
conductivity.
materials.
Do you think I can measure it?
That should have an effect.
Yes, of course. It has an
So
effect.
that